Thank you for the introduction and thank you for the invitation. I'm excited to be here, and I will be presenting my work, which is part of a larger research project between different universities and industrial partners. And like Elif said, I'm focusing on the rationalization within the construction industry. So in general, if you have a question while I'm presenting, feel free to raise your hand and interrupt me, So nowadays, with the development of new tools and new methods within the construction industry, it's quite exciting to be an active part of it. We have the saving of the information of a building in a digital model. Nowadays, we have the use of drones, of augmented and virtual reality for the monitoring, of the construction process. Sometimes they play an active role in it, and things are developing very quickly. Of course, this is unfortunately only a small part of the construction industry, because for the larger part of it, we still use many methods and processes that are traditional. And by traditional, I by no means mean that tradition is bad. Yeah, you'll see that through the lecture. When I talk about older means of construction and fabrication, I refer to the impact that this has in the environment. So despite all the process of the last years, construction industry is still responsible for 1/3 of global energy consumption. And when we talk about developed countries like the UK, this rises up to 50% when we think about the whole life cycle of a structure. So if we look at the life cycle of a structure, obviously there are many, many reasons factors that can affect it, and these are just indicative. But usually you start with the design development, construction, maintenance, demolishing, because no structure lives forever. And then the demolished materials are ideally reused, and they're used in a different context. And this, of course, is all a very small part of a much larger image. So within that process, if we manage to change even a very small bit in the life cycle of one building, we can have a much larger impact if we look at the larger image. So this is where rationalization comes into play. Does anyone know what rationalization is? So I looked it up when I started my research, because you use it, but you're like, I was trying to find the definition, and I found many, but I think the best one is this one. It's actually one of the first one, which was given in the 80s by Lindsay. He is the director of Gary Technologies, and he describes rationalization as the introduction of mathematical rules of constructability in order to legitimize crazy designs. So we will be looking at rules of constructability, and we will try to define what crazy is. So, of course, we could do it in any of the parts of the life cycle of a structure, but we would be focusing on geometry. Let's just mention here that I'm not studying how a geometry was generated, whether it's good enough for the purpose that it is trying to serve, or I'm just looking at how constructible it is. Because there is a relationship between the geometry and the fabrication. Because we know that some forms are easy to be built, and they can stand for a long time, while others are harder, right? So what defines how complex a geometry is? Well, complexity can be defined as having many parts that we cannot describe or understand or find an answer to. So this is what we are trying to avoid in construction. We're trying to have control of whatever it is we're building. And we will be particularly looking at space frame structures, trusses. So they comprise of members, sticks, which you combine with joints. And these structures became very popular after the 50s, when Mero, a German constructor, he patented a system that allowed you to have a joint in which you drill holes and then you connect members, and it was very easy to build quickly and large large-scale structures. So people started using them in large span applications. And nowadays, with all the tools of analysis and form finding and manipulation of complex geometries, we start seeing space frames being applied in large-scale structures of complex geometry. So this is the Haydar Aliyev Center of Zaha Hadid Architects in Azerbaijan. This is the Singapore Art Center in Singapore. This is the new Daxin Airport in China. I might be pronouncing it wrong. And this is the plan for the New Mexico airport. What?
It's the sad story, that's all.
That's why I said the plan for the airport. Yeah. I was careful with that. So we can see when we look at the development of space frame structures that there's a shift from this to that. So what's this, what's that? This is a singly curved geometry, and it has a constant curvature. What that means is that even if we just had a pencil and a paper, we could define the angles of the members, we could see what geometry we would get, and we would have the same angles on the top layer and the bottom layer throughout the whole structure. So the same joint throughout the whole structure, same member lengths, easy to build, great. So now we go to that, in which the curvature is not constant. It's given by an equation which is usually quite complex to understand or define. It changes a lot, and it has an important effect in the members and the joints of a structure, because they need to be different in order to generate free-form geometries. And in my research, I focus mostly on the joints, because they have a high impact on the construction. They usually, as you can see, they're responsible for 30 to 50% of the whole fabrication cost and 20 to 30% of the mass. So if we can understand or improve the joints, we can have a larger effect on the construction process of free-form space frames. So what we're going to try and understand today is, first of all, we need to study how joints are fabricated. What degree of variability do different fabrication processes allow for? So if I fabricate a joint with one process, if I fabricate 10 joints, will they all have to be exactly the same? Can they be a bit different? And if different, how much? Then we're going to try and evaluate the variability in joints, how much different the joints within a structure are, and how's this difference distributed within the structure. And finally, if we combine these two study areas, we can get a deep understanding of what actually the construction complexity of our structure is, what fabrication process is the most appropriate for our structure, and how can we actually optimize its geometry to address this issue. So, needless to say that there are many fabrication processes for joints. You can cast the metal sphere and drill holes in it. You can cast a mold and then the sphere in it and drill holes. You can 3D print the joint. You can have molds out of wax, which you use a certain number of times and then you destroy it. Many. So if we want to classify them in terms of variability, we're looking at two factors: the batch size and the automation. So batch size is how many joints do you fabricate on one go. So for example, if you 3D print a joint, every time you set up the machine, you fabricate one joint. While if you imagine like factories in which they have mass production of joints, they would press go and they would fabricate 100,000 of joints at once. So we're trying to combine the batch size with the process automation. The process automation defines how often we can actually intervene in the process. So how often can we tweak the information or provide different information for the elements that we produce. So again, 3D printing, every joint has its own file of information that you send to the machine, so every joint can be different. If you mass produce joints, then however many you mass produce, they're the same. So we're starting to see that there are two types of fabrication processes. At the one end of the spectrum, we have the discrete fabrication, in which you fabricate one element, and however many elements you fabricate with this process, they can all be different. And we have the continuous fabrication, in which you fabricate many elements and they're all the same. So in between, you have the fabrication in groups, which obviously refers to the case in which you fabricate clusters of joints, and within the cluster you have a small amount of variability of your members, and this is the most realistic scenario in practice. And like Lindsay is the rationalization definition guy, like he mentioned, when it's not feasible to have complete uniformity in joints and freeform geometries, but when you fabricate in groups, if the threshold of the joints that are the same is below a certain limit, you can make up for the cost of the joints that are too different from each other. Because obviously discrete fabrication costs more than continuous fabrication. So it's all about finding a limit. And yeah, so we will be looking at how many groups of joints do we have, and how different the joints are with each other. Of course, there are many different types of joints. There are more than 250 jointing systems, 15 fabrication firms, so it's hard to understand or generalize a way to approach this problem. If we look at the videos play, yeah, just a second, no, theoretically. Anyway, so different joint designs allow for different degrees of tolerance. And this can be either because the design itself allows the members that connect the joint to move on different planes, either vertical or horizontal, or because of the fabrication manufacturing equipment isn't 100% precise. I mean, even with a robotic arm, you do have a tolerance of 0.01 degree within a lifespan of 2 years, or even in fabrication. Because if we think of a scenario where you're on a construction site and there are two joints and the member is half a degree off, what are the chances that the people on the site will actually send the member back and ask a new one? They will probably just pull the member in place. This will, of course, induce a bending moment on the member, which is not supposed to take, but that's not our focus now. So if we combine all these tolerances of the joints themselves with the fabrication process, we can see that within a project, there's a certain amount of tolerance that you can consider acceptable, which means that if two joints have an angle difference below that limit, they could still theoretically be fabricated within the same batch. So how do you use this in practice? How can you actually make use of that and improve our designs? Scenario one, I'll show you two scenarios. Scenario one is that you're in the design development stage. You have the geometry that you want to fabricate, and you have decided on the fabrication process that you want to use. So this means that you have a fixed process and a joint tolerance. So the way you can use this approach in practice is that you can try and identify the optimal fabrication clusters. So we're going to test this on the Haydar Aliyev Center of Zaha Hadid Architects. The whole structure comprises of a library, auditorium, and a museum. For the sake of this research, we'll only focus on the museum. So the museum itself, it has 318 joints. If we consider that there's no tolerance at all, we would end up with 3,018 joint clusters. So if you look at the graph on the bottom, on the horizontal axis, there's a tolerance that you consider acceptable, and on the vertical is the number of different joint clusters that you need in order to fabricate it. And the spheres in different colors, they represent different fabrication batches. So it's evident that if you increase the joint tolerance that you allow for without changing the geometry at all, the number of clusters will drop, right? And gradually, as it increases very high numbers, you will see that you will end up with having just one very big cluster with a lot of tolerance within its members. So for the sake of this study, we consider that we have an input fabrication tolerance of 5 degrees. And this, with a 5 degrees tolerance, we have 1,067 joints with the input geometry that we had from the architects. So the goal of this is to start optimizing the bottom layer of the truss structure and try to identify the one that yields the smallest number of joints. And as designers, you can define the depth on which your bottom layer joints can move, because you would obviously have some design restrictions and structural restrictions. But the point being that through this process, you can achieve an important reduction in the number of joints that are required for the fabrication of this, without compromising structural performance. We achieved a 15% reduction in the joints. And in order to evaluate what effect this has on the visual, on the aesthetics of the structure, we will run a cross-section through our structure. On the left-hand side, it's the original structure of the building, and on the right-hand side is the optimized geometry after the optimization process. And this should play. No. Oh. No. There's a small difference. Trust me in that. So what I meant to say with that, it's not from my laptop, so the videos don't play. My apologies for that. If we read papers that describe the structure in practice, they mention that the average depth of the space frame throughout the museum structure is 1 meter. So when we ran the optimization analysis, the joints were free to move from 0.5 meter to 10 meters. So they had quite a lot of freedom, and there were many possibilities to find improved solution. The interesting bit is that the final geometry that had the smaller number of joint clusters, the depth range of the optimized structure is between 0.5 and 0.8. So it means that the visual difference between the original structure and the optimized is very, very small. The whole building covers an area of 28,000 meters. I mean, the two buildings together. So a difference of 20 centimeters in depth without compromising the structural performance can lead to a very important savings when it comes to fabrication and construction. So overall, this can give us a very good understanding of how, by looking at the construction complexity of our structures in early stages of the design, you still have the possibility to significantly improve without compromising the design. So now we'll go to a different way in which this workflow can be approached in practice, in which we are again in the beginning of the design development, at this time a bit earlier on. So we have a geometry, but we haven't decided on the fabrication process yet. So what we're trying to do is we're trying to identify which process is more appropriate, or what type of processes can we use in our structure to have an improved fabrication workflow with a smaller cost and smaller carbon emissions. So we're going to test this in the Singapore Art Center. Actually, there are two structures which are the same, and we will apply the workflow only in one of them as a case study. So the scale of it is quite similar to the one of the Haydar Aliyev Center, so around 3,300 joints. And the way we approach this is that, considering that we don't know which fabrication process we want to use yet, we don't know the number of clusters or the size of clusters that we are going to have. So in this case, we analyze our structure for different number of clusters, and we try and see how complex it would be. So in this graph, in the horizontal axis, we have the number of clusters that we analyze it for, and in the vertical axis, we have the intercluster variance. So that is within one fabrication batch, so within one go throughout the fabrication process, this describes how different the members within one cluster are. And we analyze this for 10, 50, up to 500 joint clusters, and we're trying to see how that affects the fabrication process. So we can see that obviously larger circles, if you look at the legend on the right, describe clusters which are more compact, so elements within that cluster are more alike. The vertical axis describes how compact the clusters are, and the size of the circles describes how big they are. So when we analyze our structure for 10 clusters, so the 3,300 joints, we divide them in 10 clusters, obviously we have large clusters in terms of items which are not very similar with each other. While you can see as we increase the number of clusters, the clusters become more compact with each other and smaller. So if we look at, let's say, 400 joints, it's still not easy to try and understand how the fabrication process is with this, right? Because imagine that on the vertical axis, there are 400 clusters, meaning 400 circles, overlaid the one on top of each other. So it's hard to understand, okay, where do I have most of my clusters? And are they big or are they small? So to get a better understanding of that, we try and overlay this with the frequency distribution of this clustering analysis. So we can see that for clusters which are in which the intercluster variance is small, meaning for compact clusters, these are the most of my clusters. So 259 clusters, they actually have identical members with each other. And then there are only a few clusters that have members which are highly different with each other. So this starts giving us a bit of a deeper understanding of how the fabrication process could be. In order to make use of it, we need to have an idea of what joint we're going to use. Because like I mentioned before, the joints themselves, they have some degree of tolerance embedded. So if we use a joint like the one presented on the top right of the slide, these joints, they have a very small tolerance with each other. So this means that in the clusters that have a very small tolerance, I could mass produce them, because most of my clusters, they're not different with each other anyway. While the ones that have a large intercluster variance, meaning in which I have a large variability within one cluster, it would be hard to mass produce them if I use that type of joint. So for the back part of the graph, it would make more sense to use a discrete fabrication process. So fabricate each joint on its own, which translates to that. So the dark joints in the structure are the ones that were at the front of the graph, which were all in clusters which had items which were very similar to each other, while the light blue ones are the ones that were at the back, belonging to clusters with high variance between their members. So looking at this graph, we can directly understand how our structure is. And the important thing is that this helps us identify where to use what fabrication process, because even though in practice people use only one process for the whole structure, this allows us to understand how it might be more efficient to combine them in an informed way. And going back to the same graph as before, we can see that if we would use a fork type joint, which has a much larger embedded tolerance, because this can actually allow its members to move on one plane. This would mean that I would have the possibility to mass produce a much larger amount of my clusters. So up to 120 degrees of intercluster variance, I could mass produce them. So in effect, this graph changes. So the contribution of this research is actually, the important thing is that it gives you an indication of the construction complexity of our designs. It can be applied on early stages, and it can be applied on large-scale structures. So it actually promotes an informed application of the novel fabrication processes. We get better engineered solutions, and we get a smaller cost and less carbon emissions. So if we think about the construction industry and the rationalization in it, I would like to end this short presentation being Greek with a Greek quote, that all in good measure, meaning that there is a continuous development of novel fabrication processes. We are going to use them, and that's good. But we shouldn't forget that mass production or traditional processes have benefits themselves. So we should try always and find a link and the balance into how these can be combined in an informed way to reduce the carbon emissions. That's it. Thank you. Questions? I haven't really gotten into the technical details of the structure of the tools applied because I wasn't sure how much. So if you have any questions, yeah. Sorry.
Thank you for the presentation. As you were presenting, I was thinking that this case studies reflect the current production attitudes and possibilities, but going back to a more, let's say, a theoretical approach, and I've been thinking about Mario Carpo's The Digital Turn.
Mm-hmm.
And in terms of the digital fabrication tools that now we are starting to use, like the 3D print, CNC,
yeah.
In theory, there should not be any additional cost to variation. So I was curious, what's your kind of projection into the future as maybe these tools become more robust? That in theory you should be able to have each connection varied without additional cost to production.
I'm confident that that's the case in a few years.
Yeah.
Yeah, like because there's such a big benefit of using new technologies, they're continuously being developed. But we're at this stage of history, let's say, where we still have both. And we do have the production of large-scale free-form designs. So I think that it's good to think and consider how the benefits of both. The truth is that when I started the research, everyone was like, just 3D print everything, 3D print everything. And I was like, okay, maybe that's the answer. I mean, maybe it doesn't make sense and I should focus on something else. But it's interesting that Arab had made a study on 3D printed joint steels. And it was for, they designed this roof structure in Denmark, I believe. It was in 2012, and they took a traditional joint design, and they took another optimized joint, which was 3D printed. So they did spend a lot of time. They also focused on optimizing the mass of the joint. So the final output 3D printed joint had a very complex geometry, which was complex but also materially much more efficient compared to the traditional joint. But There's a paper, there are quite a few papers on that project from Salome Galjard, and I had talked to her as well, and she mentions in the papers that because 3D printing is such a new process and it hasn't been applied, it hasn't been generalized in construction yet, they had to run specific material certification because the process wasn't certified. They couldn't guarantee that in terms of fatigue over time that the joint would perform itself as good as the traditional one, because the traditional joint, I mean, I don't like using it traditional, but I can't think of a different term at the moment. It was produced with a process which was certified. But so they had to spend quite a lot of extra money on certifying the material process. And it was interesting because after they went through this analysis, what they ended up doing is that they kept the optimized geometry of a joint, but what they did is that they 3D printed molds in sand in which they cast a steel joint afterwards. And the thing is that they use the 3D printed geometry in the mold, which is not the final product, so you don't need to certify its performance in terms of fatigue or over time. You use the same mold 20, 30 times, however many times, depends on the scale and the properties, obviously, but the actual joint is cast. So casting is a process that is certified, and then it's much cheaper and easier. So I think that's where the clever solution, let's say, come up. It's when you try and, rather than generalizing something new and forgetting completely about the old one, when you try and try and find the benefits from using both. Yeah. Yeah.
Yeah, I just wanted to say thank you. It was a very, very interesting presentation. So when you described the clusters, are you referring to, there's a variation in the numbers there. Are those a cluster being a group of like joints?
Yes.
Similar joints, so then there's an array of clusters and they all have, each cluster has a certain number of different type joint in it?
Yes, so.
And does that joint then have the variations of degrees and then how they construct that so that it fits into the piece?
So my approach is that if I have a geometry that I want to fabricate, initially I calculate all the angles of its joints, and this creates a data set of angles. So I know joint 0 has angles A, B, C, joint 1 has A1, B1, C1, etc. So in order to see how different they are with each other, you try and cluster them, and the joints that are more alike, you put them in the same cluster. Of course, this leads you in a position where at the end you would have, let's say, 5 clusters, and each cluster would have joints which are exactly the same. They have some difference. So let's say in one cluster, the maximum difference between its members is 3 degrees, whatever. So if you assume that 3 degrees is allowable, considering your joint design and fabrication process, then you would design, let's say you have 10 elements in this cluster, you would design 10 identical joints whose angles are in the 1.5. So then every joint would have a maximum tolerance of 3 degrees. Yeah. Yeah.
With the roof of Hyder-Aliyev, a similar approach was applied with the GRP panels.
Yeah.
They were clustered within a tolerance level.
Yes.
Where they can bend it in place in situ.
Yeah. Yeah, I was actually talking with LANIC engineers there, the company who had designed the New Mexico airport. And they were also saying that even though they have the technology of generating joints that are individual, like and different one from another, even if you are able to do that, then the cost of having doubly curved glazing, because they work a lot with stadium, etc., then that increases the overall cost of the structure as well. So even though I study, let's say, space frames and joints, you always need to look at the larger picture and how this is only a small part of an actual building, and that again is only a small part within its life cycle, and etc., etc. No? Okay. Thank you.